Sorry. Hi, I'm Joel. My talk is on broadband anti-reflection coatings using silica nanoparticles, and we are going to tune the anti-reflection coatings by controlling the porosity within the nanoparticle layer. So that's my work, and so I'm just going to talk about the why we are doing this. So if you need to, if you're making like a tandem solar cell and you require broadband adsorption, then you probably require a broadband anti-reflection coating. But typically, what people do is that they have just a single layer anti-reflection coating on the glass or on the silicon cell, and so there's this need for anti-reflection coatings to be broadband, and so you probably need multi-layers to actually achieve that broadband anti-reflection coating. And the problem is that they are in order to have an effective broadband anti-reflecting coating, you need a very large number of low refractive index materials like magnesium fluoride, and the lowest refractive index of magnesium fluoride is like 1.3. So the design is sort of limited by number of low refractive index materials. So what we propose is to try to create a multi-layer film that has tunable porosity by introducing polystyrene within the silica nanoparticles and then burning it off, and so you can create a void fraction within the silica nanoparticle film, and then from the porosity you can change the refractive index. And so, if you can have, if you are able to tune the refractive index and the thickness of each layer, you'll be able to design and fabricate the optimized multi-layer structure. So, so basically, the first thing we did was we just tried. We had like 10 nanometer silica nanoparticles, and we just diluted, and then we added increasing amounts of polystyrene to see how much we can control the refractive index. And as you can see, like the greater the amount of so the greater so the initial refractive index of silica nanoparticles is like 1.33 because the film itself actually has an inherent porosity of about 30%. So that's like 1.3. And then if you increase the polystyrene, it decreases. The refractive index decreases. And if you increase the dilution of silica nanoparticles, then you also increase the polystyrene fraction, then you will be able to get an even lower refractive index. So the lowest refractive index that we have achieved is approximately 1.06, 1.07, which represents like 90% porosity fraction. So when we do SEM, you can see that this is like as you have increasing dilution of silica nanoparticles, you increase the dilution increase the amount of polystyrene, you will get a aggregation of silica nanoparticles at the very end, at the very highest dilution and the highest concentration of polystyrene. So it's all well and good to make like single layer particles, but to make a multi-layer stack is actually a little trickier because we realized that when we try to spin coat one silica nanoparticle film on top of another silica nanoparticle film and then anneal it, we realized that the particles intermingle and they diffuse among each other, and then you just actually form, instead of two layers, you form a single layer with an average porosity, with the porosity that is the average of the two porosities of the two layers. So what we then did was to introduce, we have the glass substrate, and then we layer down our 10 nanometer silica nanoparticles, and then we introduce a polystyrene barrier layer that acts as a barrier that separates the two silica nanoparticle layers. And then we next layer a silica plus polystyrene mixture, and then we add another intermediate barrier, and then we add our final layer of silica polystyrene nanoparticles with, of course, an increasing with an increased amount of polystyrene. So in that way, we are able to actually achieve distinguishable multi-layers, and you can see that each, if you sort of scratch off the top layer, you can actually see the second layer underneath that. And so you can see that for each of the 3-layer structures, we see that the top layer has a higher porosity than the bottom layer, and yeah, for all 3 multi-layers. So that proves that we can actually have a multi-layer stack. So we use evolutionary algorithm, and then we design our what parameters we need for the multi-layer stack. And so for a 3-layer stack, we've managed to achieve, for a 3-layer stack on a single glass interface, we've managed to boost the transmittance from 91% to 95.5%. And then we have a broadband, a range of about 600 nanometers. So we also did the same thing for the next interface of the glass substrate, and so we are able to increase the average transmission to about 99%, with the highest transmittance of about 99.5 or 99.6%. So that's and then we tried testing it on our on some power cell. We just set we didn't try to actually like adhere the glass to the cell for this measurement, but we just set it on top of the silicon cell, and then we realized we are able to achieve like a 10% increase in the for the current. And then when we did EQE, we are able to see that the EQE spectrum actually reflects that of the UV-vis transmittance spectrum. So that proves that current actually comes from that increased anti-reflection. So in conclusion, using this technique of introducing polystyrene particles within the nanoparticle film, we can actually achieve an effective index of 1.07. And then we realized that in order to make a multi-layer structure, we need to introduce a polystyrene intermediate layer. And with this technique, we can achieve a 95.5% increase in, 95.5% highest transmission of glass. And then for 3-layer ARCs on both glass interfaces, we can get an average transmission of 99%. So in the future, we're also trying to introduce this technique on PMMA substrates, on polymeric substrates, but the problem is that we can't introduce a high temperature. So what we did was we introduced ozone to eliminate the polystyrene particles. So our first test, we have polystyrene plus silica polystyrene plus silica on the PMMA substrate, we sprinkle that, and then we introduce ozone for like 20 minutes, and then we realize that the transmission increases, which means that the refractive index has dropped, and so that indicates that we are actually removing the polystyrene. And so the next thing that we are also interested in doing is using magnesium fluoride particles, because the refractive index is smaller than that of silica. So we hopefully can get a much lower refractive index without having an extremely high porosity. So thank you for your time. Yeah.
Questions?
Yeah.
My question is for you here. You have measured your increased transmittance on glass.
Yes.
Refractive index of glass is perfect for what you use.
Yeah.
You are not going for glass, but some other way. Which is the refractive index for the layer that I'm putting inside.
Yeah.
Make a change.
Like you're talking about the difference between silicon cell and glass, right? So
first layer below your architecture coating in the cell.
yeah, like this, right? So yes, you actually have to introduce another layer, which we haven't tried that, but if we do that, that will definitely increase photocurrent. Yeah. Yeah.
Do you have a chance to investigate the polarization and angular dependence of the
Yes, I did, but I don't have the slides. But we realized that it actually is quite. It's not just. I think the design was such that we actually managed to get like 97% for both sides. For both glass. For this particular anti-reflection design, we actually got like 96% average transmission for. Sorry, I think that's a bit high. So it's 95% transmission for an angular dependence for 0 to 80 degrees. So it's also quite broadband under object incidence.
Do you know which is the lowest refractive index that has been achieved?
Yeah. For someone someone made. They use nanolithography and they managed to get like rating nanocone structures, and I think the lowest refractive index they got is 1.04. Ours is a bit higher, 1.06, 1.07. Because if you try to add even more polystyrene, the structure just becomes a single agglomerate. You don't actually have any more porosity than that, because it sort of increases. Because I mean the mechanical stability is not there anymore.
This is what I was going to ask also about what happens with the mechanical stability of these fins when you have a 90% porosity.
Yeah, it's actually not very.
This is like an aerogel.
Yeah, when we actually made our multi-layer coating, we actually didn't try to use the lowest refractive index material. Because we discovered that it's actually very hard to achieve like that lowest refractive index on the multi-layer structure. But on like a substrate, it's okay. But on the porous layer, it will not get such a high porosity. Yeah. Thank you.